Hi there. During this session I'm going to try my best to help explain the macroscopic properties of ideal gases as described with the gas laws, but trying to explain those microscopically. So considering the molecules which are involved in this and how we can explain what's happening. To start off with, let's think about what we know about the gas laws at a macroscopic level. So macroscopically, everything is defined by the gas law. Pressure times volume equals the number of moles times the universal gas constant times temperature. Now what I'm going to try and do is try and introduce each one of the gas laws, starting with Boyle's law, which shows that pressure is proportional to 1 divided by the volume, and try and explain how these things take place. So let's start off with just considering a model. I've put up my model here. Now what I'm going to do here is, for considering Boyle's law, which looks at pressure and volume, I'm going to keep temperature at a constant. So I'm going to click temperature at a constant now there. So what's said here is if I reduce the volume, the pressure increases. So if I reduce the volume, we can see that my pressure starts to go up after things have been stabilized a little bit. So I reduce the volume again, and the pressure goes up. And let that stabilize again. Now, why is that the case? Okay. Well, the reason for this the case is because the pressure is caused by the forces from each one of the molecules colliding with the outside surface. And what happens is, if I reduce the volume, it means the time taken for a particle to travel from one side of the space to the other side of the space is dramatically reduced. That means we're increasing the number of collisions. And therefore, because the change in momentum, so when a particle hits a surface and changes direction, the change in momentum causes a force acting on the outside surface. So by reducing the volume, I'm dramatically increasing the amount of collisions, and therefore at the same time increasing the pressure. So, next thing to think about, Lusac's law. So this looks at pressure and temperature, so I'm now going to just set up my model again, and I'm going to keep volume as a constant. So here the idea is that if I change the temperature, it's going to have a proportional impact on the pressure. So if I add some heat now, I'm going to add some heat to the situation. We can see as we add some heat to the situation, the pressure increases. Now the reason for that is because as we increase the temperature, the average kinetic energy of each one of the particles inside this gas goes up. And that means that with the increase in kinetic energy, the change in momentum as they collide with an outside surface is dramatically increased as well. So therefore the pressure is directly proportional to that of the change in temperature. If I reduce the temperature and cool it down a little bit, then the pressure begins to reduce down as well. Okay. Third and final example, we're going to think about Charles's law, which has the relationship between volume and temperature. So I'm going to keep pressure fixed this time. Now, Charles's law looks at the relationship between volume and temperature. As I increase the temperature, we will see that the volume expansion. That's because to maintain the same pressure we have as before, the fact that the particles now have more kinetic energy, are travelling at a greater speed, means that there has to be a larger volume for them to travel across to make sure that the overall pressure maintains at the same level. Okay. So now we've considered each one of the gas laws from the perspective of the molecules, and this is really, really, really important. Now let's just wrap this up here. So we've spoken about Boyle's law. We've spoken about Lussac, and we've spoken about Charles's law. Let's wrap up by bringing these together. Okay, so I want us to think back to the formula I spoke at the beginning, when I spoke about the universal gas law, PV equals nRT. Now, I want to start thinking about not this at a molecular level or number of moles, I want to think about the individual molecules. So therefore, if I have pressure times volume equals, rather than the number of moles, I'm going to have the number of particles divided by Avogadro's number. So the number of particles divided by Avogadro's number is equal to the number of moles. So I can replace that in. Now that now means that PV equals R, which is a constant, Avogadro's number is a constant, multiplied by the number of moles times temperature. Now, as it happens, universal gas constant divided by Avogadro's number gives me what's something known as Boltzmann's constant. So, pressure times volume equals Boltzmann's constant times the number of molecules times the temperature. And we're now able to consider gas laws with respect to individual molecules at a microscopic level.